again, is in meters squared, and y bar is the distance of the defined area with respect to the centroid axis and finally I, like you guys have known this, is the structure global second moment of area. So this is in meters, and that's the case. Q is in meter cube, and I is in meter power 4, right? And then this is the shear flow, right? And then the shear stress, over here, the shear stress will be equal to shear xy is equal to shear yx, and this will be equal to VQ. Same thing like the shear flow, only difference now you have the T. Okay, only difference that you have the T now. So that is the equation of the shear stress. Now obviously, hey, this is easy. Yeah, for now. Right? So again, these two terms over here, regardless of where you analyze, globally, the V and the I are constant. And then the Q and your T are your variables. Okay, where T over here is the thickness of the section. M. Okay. Now we are going to derive this equation. Not derive. We're going to see how this equation can be evolved. Okay. And this is where things get interesting. Okay, I'm going to use this diagram now. Yeah, I'm going to use this diagram. And it's how we derive an expression later on. You'll see. So what we are going to derive is we are going to derive that the shear xy. Okay, we're going to derive. I'll give you the endpoint. Okay, we're going to derive that the shear xy, right, is equal to 3/2, right, Vy over 2bc 1 minus y squared over c squared. We're going to derive this, right, with respect to the diagram over here. So we're going to go into the theory of shearing stress in thick wall member. Okay, in thick wall. Okay, so how we derive this, right? By knowing how to derive this expression, how to derive will enable us, okay, to set rules during the analysis. That's why deriving an expression is so critical, right? So I find this topic really, really confusing also. Only after I learned how to derive the expression, I set the rules. And believe me or not, by setting these rules, I'm able to solve any questions, okay, in the textbook or analyze any structure by applying these rules. It always works, and I'm never confused. Okay, I'm never confused. And you will see the confusion part later when we work on examples. Okay, and I'm never confused based on these rules. Okay, so regardless, whatever subject you take, this is critical. Deriving the expression, then you know the rules how the analysis is done. Or not, if you just take this as a formula, plug in, throw everything in, yeah, you're done. Okay, when I say you're done, is you're treating it like a black box and you have not a clue what is going on. Okay, so I think the core of this lecture, okay, of this course is this: as engineers, we have to be deep thinkers. Okay, deriving is critical. Okay, it's not just watch YouTube and we are done. Never like this. Okay, right, here we go. I think I need to take some drugs to calm down again. All right. So let's derive the shear stress. So we have this expression over here. Okay. So this is a cross section that you can see, right? And then this is, so what we want to do is this area is the area of interest. Okay, this is the area of interest. And for now, we will say that the shear force is coming down in this direction. Oh, the shear force is coming down in this direction now, right? So this is your Vy. Okay. So we're going to derive the shear stress equation. Here we derive the shear stress equation. Right. So what we are going to find now is our first moment of area. And you see that its z-axis is equal to a prime y. Okay. So what does this mean? So we're going to find the first moment of area about the z-axis. Okay. About the z-axis, right? And then about the z-axis, so over here, this is your area, right? So this area is the one that I've just shaded. This is the area of interest. And then y bar, right? Y prime is the perpendicular distance yes, from the z-axis. Okay, so that is why we call it QZ, right? Then I'm going to, if we were now, if the force, the shear force is applied in a different direction now, what will happen? So now I'm going to draw the same thing. All right, we're going to draw same structure. Oi. Oh, come on. Same structure. I thought my computer hanged, but it did not. Okay, so the same structure now. Everything the same, right? So again, I'll draw our axis. So what will happen now, right? If I change or we change our direction now, now our shear force is coming in the Z direction. Okay. So now the area that we're going to analyze is this area that I'm shading now. Right? So again, nothing changed. So this is our y axis, and that is our z axis. So when your shear force is in the z direction, now you want to find is the first moment of area, right? You want to find the first moment of area about the y-axis, and this is equal to a prime, okay, a prime z. Okay, so let me elaborate on this. So over here, this is the first moment of area, right? Is the first moment of area about the y-axis. So the y-axis is the axis that's going to rotate on. The first moment of area is going to rotate on. And we know that this distance is equal to what? Z. That's why this is equal to what? Z. Okay. And area, so our the shaded region is still A prime and Z. So our Z distance is basically the centroid where the area stops. So that is our Z distance. Okay. All right. So any questions so far? Are we okay? So you have to be really careful whether it's in the shear force, is it in the y or in the z direction. How you analyze your area is totally different now. Okay. Now, any questions so far? We are good. Right. So it's my mistake. This is actually y bar. Okay. So y bar is basically measured from the axis to the centroid where you stop your area. Okay, so that is your y bar. Right. So on this diagram over here, on the left hand side, the shear stress. Okay, so our shear now is on the x plane, y direction. Right, because the plane that we have now, that is the plane intersecting the x-axis, right? And the shear stress or the shear force is acting the y direction. So this is equal to the shear yx. So this will be equal to Vy over Izz Qz multiplied by thickness. Okay. So what I want you to take note is this. Okay, what I want you to take note is this. If the shear force is in the y direction, right, the first moment of area is about the z direction, and the first moment of area is about the what? Z direction. So if you are confused or if you cannot remember, so just remember this. If this is your Vy, what is of interest is your x, anything on your what? ZZ. So your first moment of area is about the ZZ, and your second moment of area is also about our ZZ. Okay. So if we look at the diagram, the VZ over here. So again, our shear now, x plane, the shear force is acting in the z direction, or the shear stress will be acting in the z direction. So this is equal to shear x plane, the intersecting plane will intersect the x-axis, right? Sorry, is equal to the intersecting plane of the z-axis multiplied by x direction. So this will be equal to Vz over Iyy Qy divided by thickness. Now this is very opposite from our what? From our moment equation, yes or no? Right? So can you all remember our moment equation which we have done earlier? So our moment equation states that what? Stress X is equal to, let's say, is eccentric unsymmetrical loading, right? So it comes out with Px over A plus by Mz over Izz. sorry, we do my first. Okay, so my. So if the moment is about y, we take the second moment of area about y axis multiplied by z plus by mz over iz